Hey, welcome to NGSS Physics. We are going to be going over lesson 1.1b, which is on the master equation and acceleration due to gravity. So if you have not already gotten out a piece of paper and a pencil, you might want to do that because we are going to be getting some equations today, and you may want to jot them down. Or if you have your physics reference sheet out, the one with the formulas on it, that would be even better. Take that out so that you can see the equations written out there and you know where they are. If not, I highly recommend starting a physics equation sheet. Let's start off by reviewing the vector versus a scalar. Vectors are quantity with both magnitude and direction. So there's got to be a number and a direction. And the direction could be a positive or a negative, depending on if it's up or down, or right or left. Or you can just put in a direction word. A scalar is a quantity with magnitude only. Examples of vectors would be displacement, velocity, acceleration, momentum, and force. Scalars, quantities that don't have direction, would be distance, speed, time, mass, and energy. Probably agree with me that time has no direction. Okay, units. As we get more and more physics equations, and then equations that have constants in them, we need to be aware of our units. For instance, when we measure distance or displacement, physicists like to use the meter because a lot of times a constant in an equation will have, if there is a distance or displacement part of it, will be measured in meters, and that way the units will cancel out. Time, scientists like to use seconds. For velocity and speed would be then meters per second, acceleration, meters per second squared. We've had all of those before, so please make sure you're familiar with them. Mass in kilograms, momentum, force, and energy we're going to get in the future. Another reason besides just canceling out units in constants, the units are important because they help you figure out what you're talking about. For instance, if you are reading a word problem and you see these units, meters per second squared, attached to a number, that will tell you that you're looking at acceleration. And so that will help you out to figure out what you're looking at. So if you see something with meters, then you know you're looking at displacement, which is either x or d, one of those things. Okay. And if you're looking at time, something with a number like 32 seconds, you know you're looking at time. So those will help you out if you remember your units. Here are the 5 kinematic formulas. These are all on your formula sheet with some variations to these formulas. For instance, acceleration and velocity. We've already had those, and we saw that we might not solve for velocity. Maybe we will solve for displacement or time. So you need to manipulate the formula around. For acceleration, you might find on your formula sheet that you have the final velocity. What if you wanted to find that instead of acceleration? How would you manipulate the formula? You'd probably say, oh, I'm going to times by t on each side and get something like this, and then add initial velocity. And it ends up looking something like that. And that's on your formula sheet. Okay, it might have vi plus at on it, but that's solved for final velocity. So keep in mind that any of these formulas, you may have to manipulate them around and solve for a different variable. A lot of times physicists don't like the fractional part of the formulas, and so you'll see them written out in linear form. This formula that is in the box is called the master formula. And take a look at this part of the master formula, VIT. VI is initial velocity. What if a car starts at rest? What is the initial velocity? The answer would be 0, and so that would be 0. Or what if something's falling and it starts and it just drops from the air? What is the initial velocity? Well, when the initial velocity of 0, that part of the equation is 0. So a lot of times the master equation can be simplified into looking like this: 1/2 a t squared. And you'll see it written like that on your formula sheet at the bottom. When the initial velocity is 0, you could drop that part of the formula off. And you might want to jot that down because you're going to be doing some practice problems like that. Okay, let's take a look at some of these variables and what they mean. If you don't know what the variables stand for, you need to know it eventually, and this is the time to really learn it. V is velocity, and you can have a final velocity or an initial velocity or a change in velocity or a constant velocity. Anytime you see v, you're talking about velocity, which a lot of you guys think of as speed, but it's speed with a direction. So it could be the positive direction, the negative direction, okay? And going up is a positive direction. Going down is a negative direction, okay? And you can assign positive and negative directions going right and left, or you can give it a term. North, south, east, west, it's up to you. Acceleration is A, and usually there's a direction involved here too because it's a vector. Is it in the positive direction or the negative direction? For right now, we're not going to worry too much about the directions, okay? But I am going to mention a little bit when we talk about the acceleration due to gravity. Displacement, okay? You can think of as a distance. And then think about, well, what kind of units go with velocity? Velocity, all of these velocities will be in meters per second. Acceleration will be in meters per second squared. Those are the units. Displacement, well, that's just meters. And here, times seconds. So keeping in mind what they mean and what units go with them, it's going to help you figure out the problems easier. So learn them, make a flashcard, make sure that you know V is velocity and the units are meters per second. And that acceleration is meters per second squared, and etc. I recommend making a data box, and here are all the possible variables you could ever have. Okay, so you can make a data box with all of them, or some of them, or a generic data box. As you're reading a question, you can write things in the data box, and hopefully it'll help you figure out what formulas to use and how to arrange things. Let's look at an example. An airplane accelerates down a runway at 3.20 meters per second squared. Those units tell me that number is an acceleration, even if they didn't tell me it was. So I am going to write in my acceleration 3.2 meters per second squared, okay? For 32.8 seconds, okay, the time. And it finally lifts off the ground, okay? Determine the distance. Well, they want to know X. Displacement and distance are very similar. Displacement just has direction involved. And it gives me a hint down here. The initial velocity is, well, if it's a airplane always starts from, 0. It's not moving at all, and then it accelerates before it takes off. And it didn't tell me the rest, but I don't really need this other stuff, I don't think. I need a formula with A, X, and T in it, and that is going to be my master equation. If you go back to that slide, you'll see the master equation looks like this. 1/2 AT squared. Now, the nice thing about this is that VI is equal to 0. So I can get rid of this part of the master equation. And really, it's just 1/2 AT squared. So I can start plugging some numbers in, and I can say that 1/2 the acceleration, which is 3.2, times the time, which is 32.8 squared. Notice that the time is, second squared, and the units for acceleration is meters per second squared, which means that I am going to end up with an answer in which the second squared cancels out, and I just get meters. So if I plug all those numbers into my calculator, I get 1721 meters. Okay? Let's take a look at another example. A car starts from rest and accelerates uniformly over a time of 5.21 seconds. That's a time. So I'm going to put that down here, 5.21 seconds. And it goes for a distance. So I'm going to go for a displacement of 110 meters and determine the acceleration. So I want this A. And it doesn't tell me, it says it started from rest. So that tells me that VI is 0. And it looks like I need an equation that has acceleration, distance, and time in it, or displacement, I should say. So that is my master equation again. VIT plus 1/2 AT squared. And again, my initial velocity was 0, so I can get rid of that. My displacement is 1/2 AT squared. It looks like I'm solving for A. So I need to times by 2 on each side. 2x, okay, is equal to at squared. And I need to divide out by t squared on each side. 2x over t squared is equal to a. Okay? Well, now I just need to plug stuff in. So 2 times 110 m divided by 5.21 seconds. Look at that. Look at all those lines. So look at the units. The units are going to be meters per second squared, which is the units for acceleration. So I'm going to plug all those numbers in. 2 times 110 divided by 5.21 squared. And I get 8.1. 8.1 meters per second squared. And you can pick which direction is the positive or negative. Take a look at another example. An object is dropped with no initial velocity, 0, above the surface of a planet, and it falls 13.5 meters. So it's going to fall 13.5 meters. Okay? In 3 seconds, time, 3 seconds. What is the acceleration? What is the acceleration? So this is seconds, okay? So it looks like this time I need time, acceleration, and no initial velocity again. So I need the master equation. And because VI is equal to 0, I'm just going to go straight to the master equation. That looks like this. Looks like I'm solving for that again. And so a minute ago, I figured out that acceleration was equal to 2x over t squared. That's what I figured out on the last slide. And so I'm going to plug those numbers in. 2 times 13.5 over 3 squared. Okay. And I get 3 meters per second. Now, if I want to assign a direction, I can say 3 meters per second down. Or because it's falling, I can say, well, going in the downward direction is negative. I can assign it a direction with that negative. Remember, with the vector, you can use either a word going down, or you can use a sign, negative, to indicate the direction. Usually in physics, when things are falling downward, okay, or moving downward, okay, we assign that the negative direction. So if you think about, plotting purposes, going down would be the negative direction. Okay, what about gravity? What is gravity? Okay, well, we know on Earth, things tend to fall down to the ground, and that is due to the attractive forces between objects and the Earth. Any object with mass is attracted to the Earth. 2 things cause that attraction to increase, and that is the more mass of the object and the closer it is to the Earth. Usually, the attractive force of gravity to the Earth is all based on the mass of the Earth. And these 2 guys right here helped us understand gravity a lot better. Sir Isaac Newton and Galileo Galilei. What is the acceleration due to gravity? Notice that it is saying it is acceleration. So acceleration due to gravity is just A. But because Earth has a certain size and it never changes, then A on Earth is always the same. And it becomes this thing called a constant. Okay? The acceleration due to gravity is based on the attractive force between the Earth and other objects. You probably remember the story about Galileo Galilei dropping things from the Tower of Pisa, and they all following at the same rate. Okay, they were all following at g, the acceleration due to gravity. No matter what they were, they would fall at that same rate because Earth is a certain size and has a certain gravitational pull. So what is the acceleration due to gravity here on Earth? It's 9.8 meters per second towards the center of the Earth. You could say that it's negative 9.8 meters per second towards the center of the Earth because that gives it now a direction, the negative direction. Or you can just say it's 9.8 meters per second downward if you don't want to use the negative sign. In physics, we typically think of things going up as positive and things going down as negative. And so sometimes that negative sign will come into play. This usually doesn't matter that much unless we are combining calculations. Things are going up and then down and then up and then down. Then it becomes a lot more important. For our purposes, we are going to neglect air resistance in our calculations when we are dropping things from the air or we're using the acceleration due to gravity. Even though there is some resistance to the air, we are going to ignore it for now. Okay, acceleration due to gravity. Well, if acceleration due to gravity, g, is just an acceleration, we can substitute g in anywhere you see an a in an equation. And then it's not a variable, it actually is a constant. It's given a number. For instance, in this equation, instead of a, I put g, and now it's just 9.8. In fact, you don't even have to put g. You can put 9.8 instead. You can put 9.8 in this equation in place of the g. Okay? When it's talking about the acceleration down towards the Earth, the acceleration of gravity, we can replace the a with the g. Now, keep in mind, that's for the Earth, that it's 9.8. If you were on a different planet or the moon, g would be a different constant. But anywhere on the Earth, the acceleration due to gravity is equal to g, which is 9.8 meters per second. And that's why those units are important, because they're in meters per second, and we need meters and seconds to cancel out. Just take a look at this. Jimmy grabs a basketball and drops it into a canyon. What will be the velocity of the ball after it falls for 3 seconds? So time down here, 3 seconds, okay? And he drops it, and you want to know what the velocity will be. So we're really looking for the final velocity here. And it doesn't give us anything else, except for, because it's falling, we know that a is really g. It's 9.8 meters per second. And you can give it the downward sign because it's going down. Or you can say, hey, I'm just going to say down. There should be a little square there. Okay? So we know what g is. Anytime something is falling, the acceleration is actually g, 9.8 meters per second. So now we need some kind of a formula that has vf in it, and that is the acceleration formula, which is the final velocity minus the initial velocity over time. Okay? See that? We can then solve for final velocity. Okay? Final velocity is going to be at plus vi. Well, that basketball started from rest. Started at 0. Okay? And so really, in fact, we could change this a into a g because I know it's falling due to the acceleration due to gravity. So really, this part goes away. And all we have for final velocity is 9.8 times 3. And you see that the acceleration due to gravity is meters per second squared. And time is in seconds. So my units for this is going to end up being meters per second. Now, if you want to put the negative on the 9.8 because it's falling, you're going to end up getting a negative velocity here. Okay? And so 3 times 9.8 is 29.8 meters per second. And if you want to put a negative because you're saying it's being pulled to the Earth, that's fine. Or you could just say down, 29.8 meters per second downward. That's what the basketball is going to be doing when it hits the ground. Okay, let's take another look. Raul drops a pile of snow from the top of a roof, 8.52 meters above. So down here, I got 8.52 meters above the ground. Okay, and determine the time. So we're looking for time down here. Required for the snow to reach the ground. So that's all they gave us. They gave us the distance, they gave us the time. But you know what? We know that it's falling. So we know what the acceleration is. Anytime something is falling, the acceleration is always 9.8, okay, meters per second. You can put a negative on there if you want to. It's up to you what you want to use. So we take a look at what we're going to use. We got gravity, we got distance, we have time. Looks like we're using the master equation, okay? And it looks like the initial velocity is 0. So the master equation is 1/2, and instead of A, I'm going to put G because it's accelerating downward. You can see something like that. So I want to solve for T. If you look on your formula sheet, I solved for T for you. Then I'm going to times by 2 on each side and divide by G. So I'm going to get 2x over G is equal to T squared. And so, now I'm going to have to square root each side, and I get that T is equal to the square root of 2x over G, like that, okay? In this case, because G is in a square root sign, I certainly wouldn't worry about the negative until after I'm all done, and then I can assign the direction at the very end, because you'll get some kind of an error on your calculator if you try to put a negative in there, okay? 8.52 divided by 9.8, and the time, okay, is going to be 1.32 seconds. Okay, 1.32 seconds, just like that. Okay, so that concludes today's lesson. I'll see you in class if you want to